going to spend about 20 minutes or so on this page, okay? And the goal is to get through kind of all the concepts we've covered this chapter, to summarize it, okay? So, here we go. Number one, first thing we did was we went and we simplified radicals, okay? I want you to tell your neighbor how to do number 1 and number 2 right now, please. Okay. So this first one, simplifying radicals. We're finding a perfect square that goes into it, so it's helpful to list your perfect squares. At least went up to 12 there. So your perfect squares, that's x squared would be those. Okay? So perfect square that goes into that. It's always best to get the biggest one if you can, but if you're not sure, you can start with the smaller ones and keep breaking it down. So root 4, root 10. Square root of 4 is 2. So you end up with 2 and square root 10. There isn't a perfect square that goes into 10. Therefore, you are done. Okay? All right. When you're dealing with exponents or multiple things under the radical, we always want to break up those things and put them in their own radicals to begin with. Okay? So when you're dealing with variables and exponents, so you can just cut it in half if you're taking a perfect square. Or since this means the square root, that means the second root. You're dividing 8 by 2, which is actually x to the 4. All right, we just don't show that 2 there, but it's there. Okay. And then 18 is not a perfect square, but 9 goes into it. So you have root 9 and root 2. Square root of 9 is 3. That's the whole reason we break it down like that. You have 3, you have root 2, and you have x to the 4th. That's 3x to the 4th, root 2. Yeah? You don't take the square root of that. You're saying, so since there are 8 of those x's in there, there are 8 of those in there. There's half of those, or 4. There's 2 sets of 4. Okay, so to get those out, you take one set out and you drop the radical symbol. So when you're dealing with a power to a variable there, you're just dividing it out. Okay. Yeah.
Why does the x4 go next to the 3 instead of going inside the radical?
Because it's not in the radical any longer. When you took the square root of x to the 8th, you got rid of it. Guys, another way of writing this, and we haven't spent a lot of time on it. We haven't spent any time on it this chapter, but we have in the past, is where you can write a square root and a power. You can write that in fraction form, in exponential form. Whatever your root is, that's the second root, and that power, you write that as your numerator, that as your denominator. That gets rid of the radical as well. Okay? So you can think of that as x to the 8 over 2 or 4. Okay? So anytime you have a root, whether it's square, cubic, or whatever, you can write it as a fraction. It actually makes it a lot easier to simplify. Okay? Number 3. Let's go ahead and try that one there. Number 3, 4, and 5, actually. Do those 3. 3, 4, and 5. All right, hey, really good discussion there. First thing I'm going to do is break this all apart. Okay, and root 75, that's root 25 by root 3. And root 25 is 5. Root 3 can't be simplified, so we're done with that. Root x to the 6th, a lot of you are doing the division piece where you just take 6 and divide it by 2. Works out well. That's x cubed. It's tougher when you have an 11, though, because that's not it doesn't give you a number that 2 goes into equally. So what you need to do is break that down into the even number right before that one. Okay, so this would now be 10 divided by 2, which is y to the 5th, and root y stays as root y. So when you're done, you've got a 5 without a radical, you've got an x cubed without a radical, and you've got a y to the 5th without a radical. You have a root 3, and you have a root y, so you put them under the same radical. That is your answer. Make sure that actually looks like y to the 5th, not the 5th root of. Yeah?
Okay, so I guess I don't really get why. So when you said it's y to the 10th, and that's in the radical, and then you break that down to y to the 5th, why is y to the 5th not?
Because you're taking the square root of y to the 5th, or y to the 10th. So you're dividing that 10 by that 2 to get that y to the 5th, and it takes it out. Yeah. Yeah.
Why is the square root of 3 and the square root of y in the same radical?
Because it's the way we write it. If you have two things under the same root, this is both square root, you just put them under the same radical at the end. Brian? You want to put it in alphabetical order. Yep. Any other questions there? Okay. Let's go ahead and I want to take a look. I know I said 4 or 5 and 6. You did those great. We'll come back to those later, or I'll put up the answers for them later. I want to move down to the next piece we did. We had fractions that we started simplifying. Now remember, when we're dealing with fractions, what was the first thing we did? Bella? We could try to simplify them first. Yeah? Yeah, put them in their own roots first is what I would do. And you could actually simplify the fractions if needed. If you look at them and you see perfect squares like these, okay, it's good to just get rid of those. Okay, the square root of 4 is 2. Square root of 49 is 7. Okay, and you're then done. You can't simplify that anymore. You're good. Remember, the whole point is you're not allowed to have a fraction under a radical, and you're not allowed to have a radical in the denominator. Okay, those are the two big things. Right here, there's a fraction in the radical. When we break it apart, we take this a perfect square, it gets rid of that radical in the denominator. Okay? I want you to try number 8, 9, and 10, please. 8, 9, and 10. Okay, you get your attention back up here. Okay, when we break that one apart, we get root 100, which becomes 10, root 9, which becomes 3, and root x squared, which 2 divided by 2 is 1, so x to the first. So we get 10 over 3x. You can't reduce the 10 thirds, so you just leave it. This one, breaking it into its separate pieces, you have root 25, root w to the 6th, and root 36. Now, many of you just won't even bother breaking it down. A lot of you will just see that all those are perfect. This part becomes 5, this part becomes w to the 3rd, and this one becomes 6. So you end up with 5 w to the 3rd over 6. Sarah? You're taking the square root of w to the 6th. W to the 6th is the same thing. The square root of w to the 6th is the same thing as w to the 6 over 2. Okay, you're dividing the 2. Those are the same thing. And that whatever your index is here can become the bottom of a fraction on your power. And whatever you're raising this to can be the top of your fraction. So w to the third. Okay, that's just how it works out. I could go through the process I showed when I introduced these, but I'll work through that with you again if you want. But, okay. Number 10, that's root 7 over root 81, which is root 7 over 9. Okay. Very good. You'll notice I've skipped all cubed roots so far. Okay? All right. So what I want to do is I want to go back through and work on our cubed root ones right now. So the first cubed root was number 6. Okay, then we have these 3 down here. I want to kind of approach all those at the same time. So I want you to try to first actually list all your perfect cubes up here with your perfect squares. Okay? Go ahead and go to 10. Perfect cubes. Yeah, some of it, yeah. Okay, number 6. Oh, actually, let's get our perfect cubes. 1. What's the next one?
8, 27, 64, 125, 216, 343. No.
Yep. Right there. Yep.
512.
512.
729. 6. 1,000. 1,000. 6,000. 1.
All right.
1,000.
Got them all? Yeah? 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So when we're looking at this, is this a perfect cube? In fact, let's break them all up first. 128. Cubed root of x to the 5th. Those are both cubed roots there. 128 is not one of our perfect cubes. You want to see if any of these perfect cubes fit into it. 64 does. Okay, so we're doing the cubed root of negative 64 and the cubed root of 2. The cubed root of negative 64 is, that was our 1, 2, 3, 4. So it's negative 4. Remember, you can have radical or negatives inside your radical as long as it's an odd root here. And the cubed root of 2, we just leave this, the cubed root is 2. So right there we have that, we have that. Now we have to deal with that 5. And so using the same process we used when we dealt with square roots, we can think of this as, let's think of this piece as x to the 5 over 3. Does it go into it evenly? No, 3 doesn't go into it evenly. All right? So you've got to pick the number closest to 3, but not greater than 3 that 5 goes into. What number is that? Right. So the other way to think, we could think of that as x to the cubed root of x to the 3rd and the cubed root of x to the 2nd, because we have 3 and 2. The cubed root of x to the 3rd is x, and this is just the cubed root of x to the 2nd. It doesn't change. So with all of our pieces there, the negative 4 is on the outside. The x is on the outside. We have a cubed root of 2 and a cubed root of x squared. That is our answer. Okay. All right. 11. And give number 12 a go. 11 and 12.
I figured out what I did with this problem. I just didn't finish the last part of it.
It should be getting a little easier.
Yeah. It's getting easier to put them in like the right format too.
Good.
For the square root of 8, it fits into 8, but you can't put that as a radical, can you? Square root.
No, this is cube root though.
So it's 2.
Yeah.
Cube root 2 even. Cube root is 2. I got this. I don't know if that's written right. It's okay if there's a radical on top of the fraction, just not on the bottom.
Correct. Yeah.
So I think I did it right.
All right, there's number 11. Hey, how many got it? Cool. So cubed root of 8 is 2. The cubed root of h to the 4th, you've got to break apart into the cubed root of h cubed by the cubed root of h to the 1st. Okay, so that gives you cubed root of h cubed is h. And the cubed root of h to the 1st is just cubed root of h. And then cubed root of 27 is 3.
Yeah.
All right. So this one we're breaking apart as well. We've got the cubed root of 81, cubed root of y squared, cubed root of 1,000, and cubed root of x squared, or x cubed, excuse me. Okay? Cubed root of 81 is it 9? Not 9. We've got to break that part down to cubed root of 27 times
2. 3. Not 2.
times 3, yeah. Okay? That part breaks apart into that. So 81 is 27 by 3, and 27 is a perfect cube. It becomes 3. Okay, so we're done with that piece and that piece now. Cubed root of y squared. Can we do anything with the y squared? Is there anything prior? Well, first 3 doesn't go into 2, and is there anything prior to 2 that 3 goes into? No. You only have 2 of them. You need at least 3 to take one out. So we can't. We have the cubed root of y squared. It just stays like that. And then on the bottom, we now have cubed root of 1,000. Is that perfect? Yeah, that is 10. And the cubed root of x cubed is?
X.
Is x.
What I missed 81.
So we end up with, if we put it all together at the end, 3 cubed root of 3y squared over 10x.
What did you do with 81 again?
81 became the 27 and 3. Yeah.
How did it become 27 and 3?
27 times 3 is 81.
Oh, okay.
And 27 is our perfect cube.
Oh.
All right. Any questions? Okay, I want to go on to rationalizing the denominator. Remember, you're not allowed to have a root in the denominator. Okay? So by the way, there's number 13 there if you want to practice it if you have downtime. But don't do it while we're doing this part here. Rationalizing the denominator. In other words, get the root out of the denominator. If this math vocab here is confusing you, write in parentheses next to it, get the root out of the denominator. That's what that means. Okay, so to get the root out of the denominator, we have to multiply by? Good. You take whatever root's in the denominator and multiply by that over itself. Remember, this is the number 1. Root 3 divided by root 3 is 1. Therefore, you're not changing the value of this. You're just changing the form. When you multiply a root by itself, root 3 by root 3 is just 3. Root 3 times root 3 is root 9. And the square root of 9 is 3. So you always, whenever you multiply a radical by itself, you always get the thing that's inside of it. It just comes out. And then on top, you have 5 root 3. You should ask yourself, can I simplify the things on the outside? 5/3 doesn't reduce, so you're done. That is your answer. Okay, let's try number 15. That time we get 2 root 2 over 2. However, can we simplify the 2 and 2? Yeah. 1. So we just call it root 2. Okay, root 2. Those are 1s. We just don't worry about them.
What happens if you put the 1 next to the root?
Oh, that's not correct format. Yeah. So we're going to break this one down. We want to write it as its actual pieces. We want to give it each part its own root. So root 2 over root 7, we had a fraction in the radical, now we have a radical in the denominator. Both are bad. So we're going to multiply by root 7 over root 7. Root 7 times root 7 is 7. And root 2 by root 7 is root 14. Is there a perfect square that goes into 14? Nope. Can you simplify the 7 and 14? Good. Yeah, one's inside, one's outside. You can't. They can't play if they're in different spots there. Okay, if one's inside, one's outside, you can't simplify. All right. Try number 17, last one. On that there. You already did it? Alex.
But I wasn't paying attention when I was doing something on my calculator.
So what you do is that you put these into their own ones, but then you're going to do the same thing that you did with the other ones, and multiply each one by 7. And once you do that, since these are both the same root, then you do 14 over 7.
Okay, good? Okay, any questions on rationalizing the denominator? Okay, we then have adding and subtracting. What's the rule when you're adding and subtracting? They have to be like terms, yeah.
Oh, those are all like terms.
These are all like. You're counting up roots. You have 3 little root 5s and 4 little root 5s and negative 2 little root 5s. So how many root 5s do you have total?
5.
3, 4, that's 7, minus 2 is 5. You have 5 root 5s.
Wow.
Now, if the roots are not the same, hey, need you to focus, please. If the roots are not the same, you cannot put them together. Okay? The only thing you can do is try to simplify them to get the same root. So in this case, root 2 doesn't simplify, but root 8 does. Everyone write what root 8 simplifies to, please.
2 times... root 2 times 2. Or root 2 times root 2. Root 2 times root 4. I don't have to say because I'm smart.
That goes to 2.
I got 10.
Okay, so the 3 just stays a 3. I don't even really need to bring it down. I can just circle it. Root 8 becomes root 4 root 2. Root 4 is 2, so I get 2 root 2. So I have 3 times 2 times root 2 plus 7 root 2. Notice I have the same roots now. What is 3 times 2? 6. So we could call that 6 root 2 plus 7 root 2, which is 13 root 2s.
You went too fast.
13 root 2s. Okay, give number 20 a go. I'll be walking around if you need help. Okay, we don't have like roots. Can we break down 7? Can we break down 14? No. Any perfects that go into it? No. Any perfects that go into 28? Yeah. So this becomes root 4 root 7. The 2 just stays, as does the 5 root 4, or negative 5. root 14, as does the 6 root 7. Okay, this part becomes 2 root 7. Okay, so those are all my pieces now. If I put them together here, I have 6 root 7 minus 5 root 14, and then 2 times 2 is 4 root 7. What can I do with that? Yeah. Combine like terms. 10 root 7s minus 5 root 14s. I can't go any further than that because I can't make 14 and 7, those roots become the same. Okay? Questions? All right, turn it over. Conjugates.
I don't like the ones where you have to go like distribute.
Okay. Hey, you guys, it's taking a little longer, but the conjugates, note the difference between this type of problem, like number 14 where you have a radical in the denominator, and this one where the problem is you also have a radical in the denominator, but you have something with it that's being added or subtracted. Whoa. So when you have that, you've got to multiply by the conjugate. And the conjugate, if you're using this pattern, the difference of two squares, a plus b times a minus b, you can get a squared minus b squared. Just whatever that is squared minus whatever that is squared. So if we thought of this as our a and our b, we have a plus b right there. We need a minus b over here. And then whatever's on the bottom, we're going to also put on the top. That way we're still multiplying by 1. It's just in a different form. Yeah.
What if over there it's a minus?
Then it would be plus. So like on number 22, since it's subtraction over here, on this side we'd have to put root 7 plus root 3.
Okay.
All right, so when we multiply number 21 out, we get 3 times 3, which is 9. If we're following the pattern, we just have to multiply the a's by each other and then the b's by each other. So 3 times 3 is 9. Root 2 by root 2 is? Root times itself, you get 2. You get the thing inside. And then it's subtracting, right? That's what this pattern says, difference of two squares. And then on top, we have to distribute. That's 21 minus 7 root 2. Then simplify. We get 21 minus 7 root 2 all over 7. Okay, any questions up to there? Why can't we subtract 21 7? Because the 7's counting root 2's. The 21's just counting units. They're not. This has a root 2 on the end. Okay? Can we simplify it? Yeah, you can simplify it because 7 will go into both 21 and 7. If 7 only went into 21 and not this over here, then you couldn't simplify it. But since it does, you can. That would become 1. This would become 3, and this would become 1. So you get 3 minus root 2 all over 1, which is just 3 minus root 2.
This light makes brain sense. Brain sense.
Okay. I want you to try to finish up number 22. Root 7 by root 7 is 7. Root 3 by root 3 is 3. 9 root 7. 9 root 3. All right.
Oh, you can't.
Think we got it?
I am sort of things.
Okay, if you want to try another one, you can try number 23, but I'm going to move on to the bottom part. Yep.
Can the bottom number be a negative number?
Yeah. Okay, last part. Number 24. Everyone do 24. We're going to do two problems here, 24 and 26. I have to do 25 and 27 as well, because those kind of get a little goofy. But. So 3 times 2 is 6. You multiply the things outside together and then the things inside together. 5 times 2 is 10. 3 times 6 is 18. And root 5. Can you simplify root 10? Perfect square that goes into 10? 2 is not perfect. No. It's perfect square that goes into 5. No. Can you put 10 and 5 together? No. So you're done.
Oh, it wasn't. Oh.
So actually, rather than going 26, let's do 25 real quick. So multiply it out, distribute it first. Everyone get 2 root 18, 10 root 12? Okay. Can we simplify root 18? Yeah. We've got to bring that 2 down. So root 9 is 3. So we have 2 times 3, root 2, which is 6 root 2. Can we simplify root 12? Root 4 and root 3. Root 4 is 2. So we have 10 times 2, 20, root 3. Can we put root 2 and root 3 together? Nope. So we're done. All right. Any questions there? Last piece, and I'm actually just going to do 27. 27 is the harder of the two, so let's do 27 here. Remember multiplying binomials? FOIL? First, that one times that one. Everyone write down what that is. That gives us 16 root 3. Hopefully you got that. And then this one times that one. Write that down. Okay, hopefully you got 40. This times that. Now whenever I have a negative, I try to circle it. Negative root 3 times 2 root 3. Multiply the roots. Root 3 and root 3 is? It's 3, right? Root 9, which is 3. Okay. It's negative times positive. That's negative. Root 3 by root 3 is 3. And then we have that 2 also. So we have negative 2 times 3 there. And then we have negative times positive is negative. Root 3 by 5 is 5 root 3. And now we've got to put all the stuff together that we can. Okay, 16 root 3. Can I put it with anything else? Yeah, 16 root 3 and 5 root 3 is 11 root 3s. Okay, can I put anything together with the 40? Yeah, this would be negative 6, right? 2 times 3 is 6. So 40 minus 6 is? That is positive 34. So we have 11 root 3 plus 34. There you go.